All right, so a thin wire has the shape of the first quadrant part of the circle with center of the origin and radius a. The density function is rho xy is equal to kxy. Find the mass and center of mass of the wire. All right, so the first thing we want to do is we want to reparameterize our x and our y. Now, we're not given an x or y function, but we do know that because we have the shape of a circle, we can put things kind of in terms of, and basically in terms of polar coordinates, where x is going to be a cosine t, where a is the radius, and t is going to be, the time it takes to go from the positive x-axis to the y-axis, and y, of course, is going to be a sine of t, where t is going to be between 0 and pi over 2. The first, basically the two angle measures that make up the first quadrant. All right, now we can go ahead and find our ds. That way we can go ahead and plug it in. And our ds is going to be the square root of, so the derivative of a sine of t is just a cosine t. So a cosine t squared plus derivative of a cosine t is negative a sine t. And so I have that there squared. Because we're both squaring cosine and sine, it's just going to give us 1. And we're going to have a squared left underneath the radical. So the square root of a squared is just going to be a. So we have a dt. Now I'm going to go ahead and subset into my mass function. So my mass is equal to the integral from 0 to pi over 2 kxy. So kx cosine t times a sine t. I'm sorry. Hopefully I said a. Times a dt. I'm going to go ahead and pull out my k's and a's because those are just constants. And so I'm going to have ka cubed on the outside. And then I can go ahead and on the inside, I'm going to have cosine t times sine t. Well, the derivative of sine is cosine, so I can say, oh, that's just 1/2 sine squared t, and go ahead and do the integration. So I'm from 0 to pi over 2. And now, go ahead and plug it in. Pi over 2, and the sine is 1, so I'm going to be left with 1/2. Sine of 0 is 0, so I have 1/2 minus 0, which is 1/2. So my mass is 1/2 k a cubed. All right, so that's the total mass. Now let's find the center of mass. So I do the x bar. So x bar is going to be 1 over m. So I just took the reciprocal of that. So it's going to be 2 over ka cubed times the integral from 0 to pi over 2. Now, because we're doing x bar, we multiply by an additional x. That's why I have a squared cosine squared t. K a sine t a dt. All right, I'm going to go ahead and pull out ka to the 4th. When I do that, ka cubed is going to go away. The only thing that's left is 2a. Then I have the integral from 0 to pi over 2. Cosine squared t sine t. This is what's left. And again, the derivative of cosine is negative sine, so I need a negative, and I also need to add in another cube, so negative 1/3 cosine cubed t from 0 to pi over 2. When I plug in pi over 2, I get 0 for the first part. When I plug in 0, I get 1, so I get plus 1/3. So 2a times 1/3 is 2/3 a. When I do y bar, I get the same thing. I have 2 over ka cubed. So this is just dividing by m and multiplying by the reciprocal of the mass. The integral from 0 to pi over 2. Ka cosine t. Now there's, I'm multiplying by an additional y, so it's y squared. So a squared sine squared t a. Pull out ka to the 4th, and I'm going to be left with 2a on the outside again. The integral from 0 to pi over 2. Sine squared t cosine t. Again, derivative of sine is cosine, so I can have 1/3 sine cubed t. Plug in pi over 2, I get 1, so I get 1/3. Plug in 0, I get 0, so 2a times 1/3 is just 2/3 a. And so there's my center of mass. Center of mass is at 2/3 a, and my total mass is 1/2 ka cubed. All right, what if we have a piecewise smooth curve? So again, like piecewise defined functions, you have multiple functions that make up the total function. What if we have a bunch of curves that make up the total curves? Well, that's okay. We can just separate it, and we'll just take each, by turn. So like C sub 1 is a line segment. C sub 2 is, looks like a semicircle. C sub 3, another line segment. C sub 4 looks like another, circle. C sub 5 another line segment. So we can just break it up and continue to go on. Now, two other line integrals are obtained by replacing delta s by either delta x, where it's just the difference between two x's, or delta y, the differences between two y's on the curve. In the formula for line integral, they are called the line integrals of f along c with respect to x and y. And so here we have, if I'm looking for, notice this is the curve of c, but just for dx. If it's just for dx, then it's going to be x prime of t. Now again, this is not really for, this over here, just for what's above. Or the integral of f of xy dy, then we're just taking it times the integral of y prime of t. All right, so this is just for the next example.